likes to recommend lots of books. Chaos is one of them. Alice in Wonderland was awesome.
Alice in Wonderland?
Yeah, he talks about the mathematics in that book, and it's so awesome. The writer was a logician. Anyways,
A logician or a mathematician? Who's a
he
mathematician?
taught mathematics, but they know him as a logician.
Alright, well, let's start product topologies. So, quick refresher on what we talked about last week. Do you remember?
Was subspace topology?
Subspace topologies. So chapter 3, we're going to be looking at ways that we can create topologies from existing topologies, right? And one of the things we talked about was, if you think about, remember talking about the Taurus, and how, you know, we might have had a tough time up front trying to think about how to put a topology on this thing. But if I think about this thing as a subspace of R3, and then I think about the basis on this surface as the intersection of open balls with that, now we have a great intuition for a topology that we could have on there. So we called that the standard topology on there, when this is a subspace of R3, and then we knew right out the door that if I were to take some open patch on the surface of this thing, that would be an open set net topology. And if I were to take some closed patch on the surface of that thing, then that would be a closed set net topology. And we got that all for free just from our intuition already about R3. So that was subspace topologies. The one that we're going to talk about today is product topologies. Now, I warned you last week that you better be very, very comfortable with what this means when we're talking about two sets, taking about the cross product of two sets, because ultimately that's what we're going to be doing. We're going to be taking two topological sets, applying some sort of cross product to them, and getting a resulting topology from it. So that's the way subspace topology was like looking at smaller topologies and a bigger topology. The cross product topology is going to be taking two topologies and sticking them together to get a bigger topology. And then the last one that we're going to be, oh, you guys don't have books. I'm going to say it's a section that I recommend you read, but
I can make copies for next class if you need it.
well, they would have wanted to read it before next class, because then we're going to be talking about quotient topologies, which is much more relevant. We'll be talking about quotient math, which is going to be our first real taste of actually finally applying functions to sets instead of just talking about sets all the time. But we'll get to that when we get to it, I guess. All right, so today, we're going to be talking about the product topology. And for establishing our intuition for taking the cross product of two sets, we usually keep a picture like this in our heads. So if I want to think about the set A cross B and what that looks like, even though A isn't really some continuous interval and B is not really some continuous interval, it helps us to keep our intuition straight about what these sets look like if we think about A as an interval, B as an interval, and then their cross product being this area. Purely for intuition, right? Because what are we doing? We're assigning to every point in A all of B. And that's what we do over and over again. So when I'm looking at A cross B, that's every possible ordered pair I can make. This is equal to the set of all ordered pairs A comma B, such that little a came from big A and little b came from big B. Right? Mm-hmm. And so if I were taking, keep it really small, 1, 2, cross with the set A, B, then this is equal to the set. We take 1 and assign it everything in here, and then 2 and assign it everything in here. So I take 1 and I'm going to assign it everything in here. So 1 and I'm going to assign it A, and then 1 and I'm going to assign it B. Okay, so I assign this to, I assign 1 to everything in here. Now I assign 2 to everything in here. 2 to A, 2 to B. And so that's why this picture kind of helps us, because we're thinking about to any point in A, little a, I assign all of B to that point. So these are all the points with A as their left-hand value, little a there. Make sense? Okay. And it's just as valid to think, okay, let's think about some little point B here. Now these are all the points I get assigned to B. Make sense? And so it's helpful in our intuition to think about it. Sometimes, even though it is A cross B and it is this, we're taking elements from here and assigning them to elements in here. Sometimes it's helpful with this picture to think about assigning to some point in B a bunch of A's, rather than to A a bunch of B's. Make sense? Going back and forth thinking about it that way? Okay, now I decided to also draw this picture up. There's two terms that we already proved in the past that we're going to have come up today, so I wanted to draw a picture of them to at least make sure we reestablish your intuition. So, what I'm drawing here, I'm showing that, so A1 and A2 are subsets of the same set, and B1 and B2 are subsets of the same set. With me so far? Mm-hmm. So what I want to show is that A1 cross B1 intersected with A2 cross B2 is the same thing as A1 intersected with A2 cross B1 intersected with B2.
Well, you point to the pictures while you're
Yes.
doing that.
I was going to come up with a way to first try to make that make true sense, but maybe we'll just go straight to the picture. So A1 cross B1, that's A1 cross B1, that's this square.
Okay.
Intersect A2 cross B2, here's A2, here's B2, that's this square. What's their intersection? That's this little intersection crossed with this little intersection, that little rectangle. You see the little rectangle where they both overlap right here?
Yeah.
So that's what this set is, and that's what this set is. I could have done A1 intersected with A2 first to get that little interval, and B1 intersected with B2 first to get that little interval, and then crossed them, getting that rectangle. Or I could have crossed them first to get this square, crossed those first to get this square, and then taken the intersection of the squares. Gives me the same thing. There's the picture for it. Make sense?
When you're saying they're equal to each other?
Yes, these are the exact same thing.
Okay.
Because, let's look at it one more time. A1 cross B1, that's this square. A2 cross B2, that's this square. Rectangle, not really square. So their intersection is that little teeny rectangle.
Oh, okay.
Now let's look at this one. A1 intersect A2, that's this little interval. Here's A1, here's A2. A1 intersect A2, that little interval. B1 intersect B2 is that little interval. Now take the cross product of those two little intervals and you get that rectangle.
Okay.
Okay. So intuition, getting us through the door thinking about these cross products. So now what is the topology that we put on the cross product topology? Now, it's tempting to think, we'll call a set open in, well, let's go over the definition first and then I'll point out why it might not be what you would have guessed. So let x, y be topological spaces and let x cross y be their product. So we got two topological spaces and x cross y is the product of just the set x and the set y. With me so far? So now we're going to assign a topology to that space. Then the product topology on x cross y is the topology generated from the basis beta. Beta is equal to all the u cross v's you can make where u is open in x and v is open in y. Pick any open set in x you want, pick any open set in y you want, cross them together. That is a basis element for the cross product topology. Do we remember what a basis is?
It's an open subset. Right? Or, yeah.
It is a subset of open sets.
And
What's so special about the basis?
It's all
The
the
neighborhoods are like,
it's all the open sets, isn't it?
No, that's the topology. The topology is a set of all open sets. That's the definition of a topology. A set is open if and only if it's in the topology.
well, when you
So what does the basis help us do?
it creates the topology.
It creates the topology, it generates the topology. Any union of basis elements is open. So the basis elements are themselves open, and any union of basis elements are open. And the analogy we used is thinking about the Lego pieces. We said if you think about basis elements being all the different types of Lego pieces, and we want our topology to be Lego structures, then we want our topology to be Lego structures. then Lego structures is a set of all things that you can make when you put together Lego pieces or when you union those basis elements. Make sense?
Mhm.
So this is a basis for our topology. This is not our whole topology, it's just a basis for it. Any union of these things, we're also going to call open. Now you might have been tempted in looking at this, why don't we just call a set open in X cross Y if I can write it as a product of two open sets, X and Y? Right?
Yeah.
Do you see what I'm saying?
No.
So we made our basis the set of the cross product of all open sets. Right?
Yeah.
And that gave us a basis. We didn't say that's the whole topology, that's just the basis. If you go back and you think about the subspace topology, so if we had A is a subspace of X, what's the subspace topology on A? It is equal to the set of all open sets intersected with A, where U is open in X, or where U is in tau, we'll call it X. That was a subspace topology. The topology on A was equal to all the open sets in X intersected with A.
Yeah.
And yet we are not saying that the topology on X cross Y is equal to U cross V, where U is in the topology on X and V is in the topology on Y. This is
You're
not
saying
what we're saying.
it's a
We're saying that
basis.
this is just the basis. This isn't all the open sets. This is just a basis.
But can't you union all your bases up and get that same thing?
Yes. So this is a smaller, this would be a more limited topology than what this gives us. This gives us a bigger topology, right? If we tried to make this a topology, then these are the only open sets. If we make that the basis, then those are open sets, and any union of those things are open sets.
Okay.
Why do we want that? This exact picture will help us think about why we didn't do this and why we did this instead. So imagine that A1 and A2 are open in X and B1 and B2 are open in Y. You with me so far?
Mm-hmm.
Then, if we had this thing, then notice that we would want all this, the union of all these squares here, to be an open set in the resulting topology, right?
Yeah.
But this isn't necessarily expressed as an open set crossed with an open set, because I don't have this corner and I don't have this corner. Do you see what I'm saying?
Slightly.
So notice, so you're okay with, okay, here's A1 cross B1, right?
Yeah.
Which would be open if this was our topology.
Yeah.
And here's A2 cross B2, which would be open if this is our topology.
Mm-hmm.
But now notice that we can't call the union of this whole thing open. Why can't we? Because it's impossible for me to pick one set here and one set here such that the cross product gives me that. Because any cross product that gave me all these points would include this area down here and would include this area up here, which aren't included in that picture.
Right.
So there's the subtlety why we can't just do this. Because then that would make so that this thing was open, so this in fact doesn't give us a topology, like we might be tempted to think it would. Make sense? So when we just make that the basis, though, then we're fine. And we're going to find out that we have a more natural way to talk about the basis. Rather than thinking about the basis as the cross product of all open sets, we're going to actually be able to say that the basis is a cross product of all basis elements for the other sets. And that will in fact work. So that will be the natural way, but this is the definition so far.
Okay.
Make sense?
Yeah.
Okay. So let me see my note here. Not all open sets in product topology are products of open sets of. Yeah, that's what I was mentioning up here. Okay. Yeah, that's note that I just went over. Get rid of that, get rid of that. And guess we'll do a couple theorems now. Okay. So the collection beta, okay, so notice I just said that it's a topology generated from this basis. Well, we need to justify that this is a basis.
Okay.
So that's the first proof, justify that this thing is in fact a basis. Now how do we show that something is a basis? What are the two requirements?
That it's open,
That it's open.
and the union of basis elements are open.
I think one of them is that if you have two open sets, then their intersection, in their intersection for any point, there's a basis element surrounding that point that just stays within that intersection.
Very close. So that's the second condition. So the first condition is really easy. It's a basis element if for all little x in the space we're talking about, there exists a basis element in beta such that x is in bx. So first off, I need every point in my space to be in some basis element.
Okay.
Otherwise, obviously, I couldn't use basis elements to generate my whole space. And my whole space is an open set. So that was the first requirement. That was the easy one. The second one is one that Emma was thinking of. It's that if I have B1, if I have two basis elements, B1 and B2 in beta, such that their intersection is not empty, that implies that there exists a third basis element such that that third basis element is a subset of B1 intersect B2. Do you remember that?
Yeah.
One of the ways that we said this, so you actually mentioned the point, which is fine too. So if they don't intersect, then another way we could say that is then for all x in the intersection, there exists bx in beta such that x is in bx is a subset of the intersection. So you can think about it this way or this way. They're both saying the exact same thing. Sometimes we try to prove it this way if we can, but if it's hard to just show directly that there's some subset of the intersection, then it's easier to just grab a point and show that I can find a basis element. So, but those are both saying the exact same thing, right?
Okay.
I'm just saying for every point in the intersection, I can find a basis element such that the basis element is a subset of the intersection. That's the same thing as, oh no, it's not the same thing. No, this is how we have to say it. Just because I can find some basis element that is a subset of their intersection, I need to be able to do that for every point. When I wrote this, I was thinking equals. So that's a special case of this. So we try to prove it this way if we can. This is our fallback if we can't do it directly like this. So those didn't say anything. This is correct. This would only be a special case. So for every point in the intersection of two basis elements, there exists a third basis element containing that point such that it's a subset of the intersection. And the picture we had for that is if I have B1 here and B2 here, then for any point here you pick, I can find some small enough basis element around it such that the basis element is still a subset of the intersection of those sets. Okay. So, those are the two conditions that we need to meet. So let's do the first one. One, observe that x cross y is in beta. Okay, so all the points are in a basis element. How do I know x cross y is in beta? What is beta?
It's a cross product of open sets.
Right, if I can find an open set in X and an open set in Y, then they're cross products in beta.
Yeah.
Is X open in X?
Yeah.
Is Y open in Y?
Yeah.
Then they're cross products in beta. So now I know for sure that every point is in some basis element. Right?
Yeah.
Okay. So now, assume, how do I want to say this? Let me look back at my topology. So now I want to start out and say, assume that we have two basis elements that intersect, and so that there exists a third basis. So, here's how I want to start this. Now, let B1, B2 in beta such that X is some point in their intersection. So they don't have an empty intersection. You with me?
Yeah.
Now, what does a basis element in, what do I know about X? How can I say this? Since B1 is a basis element, it has to be open in X.
Yeah.
And since B2 is a basis element, it has to be open in Y. Right?
Yeah.
So I know that B1 has to be some union of open sets in X, and B2 has to be some union of open sets in Y. So since
So you
B1,
there's an open set in X and there's an open set in Y that contains little x. Because it's in its intersection.
oh, I said that word, sorry. B1 is a cross product of open sets in X and Y. B2 is a cross product of open sets in X and Y. So since X, maybe to help us keep track of the fact that we're talking about a cross product, I'll call the point X comma Y in that intersection. So since B1 is since B1 in beta, that means that there exists U1, U2 in the topology on X. Oh no, U1 in the topology on X and B1, no, I guess I'll call them. U1 in TX and U2 in TY such that XY is in U1 intersect U2. You follow that?
No.
Okay. B1 is a basis element.
Yeah.
Yep.
So it is a cross product of two open sets.
Yep.
U1 and U2, where U1 is open in X and U2 is open in Y.
Okay.
And I know that XY is in B1, so XY is in the intersection of these two sets. The cross product, not the intersection, my goodness. The cross product of those two sets, right? Word or pair comes from a cross product of two sets.
Yes.
And blah, 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 blah. XY is in V1 cross V2, where that's open in X and that's open in Y. Same exact reasoning for B2.
Right.
You with me?
Mm-hmm.
Why do you need V1 and V cross V2?
So I know that XY is in B1 intersect B2, and I know that B1 has to have two open sets cross product together to give me it, and I know that B2 has to have two open sets cross product together that get it.
Okay.
Since XY is in the intersection of those two things, then XY is in both those cross products. So, right. then xy, maybe I'll name the thing so I don't have to rewrite it again. Let v3 equal u1 cap v1 crossed with u2 cap v2. Right? U1 is open in X, V1 is open in X,
Yeah.
U2 is open in Y, V2 is open in Y. So I did an open set intersected with an open set in X, and an open set intersected with an open set in Y.
Okay.
Okay. Then I know that X is in B3. How do I know that? Sorry, not X, XY. I know XY is in B3. How do I know that?
Because it's in this cross product.
Yeah, XY was in U1 cross U2. So X was in U1, Y was in U2. And XY was in V1 cross V2. So X was in V1 and Y was in V2. So I know that X is in U1 and V1. So X is in U1 and V1. And Y is in U2 and V2. Y is in U2 and V2.
Yes.
So X comma Y is in B3. There's our basis element that we found. And this is going to be a subset of B1 intersect B2. Right? Obviously, everything in that, well, let's look at this for a sec. Everything in there is definitely in U1, and everything in there is definitely in V1. And everything in there is definitely in U2, and everything in there is definitely in V2. So B3 is for sure a subset of B1, and B3 is for sure a subset of B2. So B3 is going to be a subset of their intersection. Is there anything weird there?
B3 is a subset of their intersection.
Yes.
Even though you don't know that.
So let me write it out down here to, I kind of ran out of space, so I kept going fast, but B3 is equal to U1 cap V1 cross U2 cap V2, which is going to be a subset of U1 cross U2, and it's also going to be a subset of V1 cross V2, which is equal to V1, which is equal to V2. So B3 is equal to this. This is obviously a subset of this, and this is obviously a subset of this.
Yes, but how do you know that B3 would be in their intersection?
If B3 is a subset of B1 and it's a subset of B2.
Oh.
Okay. Any other questions? Sorry, I kind of squished it in there, but I think it makes sense, right?
I think so.
Yeah.
Feel free to ask any questions. We don't have a ton of material to cover today, so. So there's our first proof. Okay, so this thing beta is in fact a basis. Got that covered. So now what's next? Okay, now the more natural way to think about it. So now we're going to prove, okay, if beta sub x is a basis on x and beta sub y is a basis on y, then beta equal to the cross product of those two bases is going to be a basis for the product topology on x cross y. So now, notice how I had it over here. Over here I said beta is equal to u cross v, where u is open in x and v is open in y. That's what we initially started with to get the product topology. Now I'm going to create a different beta. I'm going to say beta is equal to u cross v, where u is a basis element on x and v is a basis element on y, and that's in fact good enough. So we don't need to use all the open sets in constructing this basis. We just need to use the existing basis elements to construct this basis, and we still get the same topology. Does that make sense what I'm saying?
Yeah.
So you're saying like that basis is a subset of another basis?
So this basis is going to be a subset of the basis we have here,
Yeah.
and it's still going to be a basis. So we don't need all this. This is enough to get us a topology that we want.
Okay.
So we're not going to want to show that this is a basis the way we did it there. We're going to want to use, I can't remember what it's called, theorem like 1.13, I think, something like that. Same one we used last week, which is ultimately using the union lemma. What I'm going to do is I'm going to show that for any open set, we already have a U and a V, so we'll call it W. I'm going to show that for all W's that you can pick in the topology on XY, on X cross Y, and for all points, I'll call it P, so we don't forget that it's two-dimensional instead of one-dimensional, in that W, there exists B sub P in beta such that P is in B sub P is a subset of W. So let me read this in English to help it make sense. If I can show that for any open set you pick, and for any point in that open set you pick, I can find a basis element that contains that point and is a subset of the open set, then my collection, beta, is a basis. Does that make sense what I'm saying? Let's draw a picture. So, pick any open set you want, W. Okay? This could be any open set. We know nothing about it except for it's open. I need to show that for any point in here you pick, X. I can find a basis element, B sub X, such that B sub X is a subset of W. Then using the union lemma, W is going to be a union of all those B sub X's for each X in there. So then I just really showed any open set W you pick can be constructed from a union of these sets, therefore a union of these sets, or therefore the collection of these sets is a basis. Does that make sense what I'm saying?
Yeah.
Oh, okay. Yeah, we've used this theorem like a lot of times. So we'll use it once again. Okay, so one, let W be open, comma, and let, I think I'll have to mention the individual points, I don't know, so we'll just name it this way. So let X, Y, and be any point in W. 2, since X, Y is in W, what do we know about open sets W so far in this product topology?
So far?
Yeah. So far, what information can I use about what information do I get when I know that W is an open set?
Doesn't that mean that there's two open sets that correspond to make it?
Not necessarily to make it. It means that it can be constructed from this basis over here.
Yeah.
So there had to be some open set U that contained X, and there had to be some open set V that contained Y, such that U cross V was a subset of W. It's probably not equal to W, but it's at least a subset. The same way that this weird picture here is just a subset of this set cross this set. Okay, so since X, Y are in W, there must exist U in the topology on X and V in the topology on Y such that X is in U, Y is in V, and U V is a subset of W. So since this is a point in W, there must have been some basis element containing the point. And these are what basis elements look like so far. Some basis element from this basis, not from the basis we're talking about. We're just proving that this is a basis. We're given now that this is a basis. So since this is a basis for the product topology, and since W is open in the product topology, I know that there, and since this is a point in W, I know that there must have been a basis element containing that point. Basis elements look like this. You follow all that? Okay. Then there must exist Bx in the basis on X such that X is in Bx is a subset of U, and there must exist some B sub Y in the basis on Y such that Y is in B sub Y is a subset of V. So talking about different topological spaces now. Now I know that U is an open set in X and V is an open set in Y, right? Since U is open in X, then, and since little x is in U, so now I have little x is a point in U is an open set in big X. So since U is an open set in big X, then there must exist some basis element in big X's basis. Sorry. There must exist some basis element in the basis on big X such that X is in that basis element and U, and that basis element is a subset of U.
Yes.
Reminder, let's go back and look up what we're saying here. Back to the very beginning. I know that beta sub X is a basis for the topology on big X. And I know that beta sub Y is a basis for the topology on big Y. I'm given that. Thirdly, I know that this thing over here is a basis for the product topology on X cross Y. W is open in the product topology X cross Y. So there must be some element in here, some combination of U and V, where U is open in X and V is open in Y. For every point in W, there must be some basis element over here containing that point. W is a union of these things. X comma Y is a point in W, so there must be a U and a V containing the point X comma Y. You follow that? So that gets us to here. But now, don't lose track of the fact, overall we have three different topologies that we're talking about, right? We have the topology on X, we have the topology on Y, and then we have the topology on X cross Y. There's three topologies that we're talking about. I know that U is open in the topology on X, V is open in the topology on Y, W is open in the topology on X cross Y.
Okay.
Since U is open on the topology on X, and since little x, that's a little x, is in U, then there must be some basis element in the topology on big X containing that point. That's what we're saying here. Such that that basis element is a subset of U. U can be expressed as a union of basis elements on X. Similarly, V can be expressed as a union of basis elements on Y. Good? Am I overstressing it? Okay.
No.
Then, we'll call it B, we'll just use regular B for the, in here. So then B equal to What am I going to have this equal to? I'm going to have it equal to bx cross by is in beta and x comma y is in B is a subset of W. And we're done. So I found some cross product of basis elements, one from X and one from Y, such that it was a subset of W. And that was our definition of this beta. This beta is equal to, I should have done U cross B. Should have done something like B1 cross B2. Let's rewrite out what this is so it's not confusing in terms of opposites. This beta was B1 cross B2, 2, such that B1 was a basis element on X, and B2 was a basis element on Y. So I needed to show that for every point in W, I can find something in here containing that point that's a subset of W. This B is a cross product of basis elements, so it's in here, and it's a subset of W, and it contains that point. We're done. I can find one of these B's for any X, Y you pick in W. So if you union up all those B's, you'll get W. I can do that for any open set W. So I just really showed that any open set W you pick is a union of these basis elements, these B's. And these B's all are in beta. Sorry.
So that B, that's not a topology, is it? The big B?
No, that's a basis element.
Okay.
That is a member of this beta.
Okay.
I found a member of this beta containing the point X comma Y that was also a subset of W. That's all I need to do. It's just since we're talking about three topological spaces here, it's easy to get mixed up in which one we're talking about. Is there any questions about that? Do we need to re-go over it from the top, or do you think you got it and I'm over-explaining, or flip a coin?
I think we should move on.
do that.
Move on? Alright. So,
But what does your note thing mean? Note generalizes?
oh, thank you. So, it generalizes. So if I wanted to create a topology now on X cross Y cross Z, the topology I could use would be generated from the basis equal to the set of B1 cross B2 cross B3, where B1 is a basis element on X, B2 is a basis element on Y, and B3 is a basis element on Z. And for higher order terms, it works the exact same way. If I want to cross 10 together, I can use the same basis. So now, if I were to ask you to look at some space, R20, it's perfectly valid to say, okay, what's the basis for R20? We already know we can look at it as 20-dimensional open balls. That's one way we can look at it. The other way we can look at it is
R cross R.
an open interval cross with an open interval 20 times.
Yeah.
So that gives us like a 20-dimensional rectangle rather than a 20-dimensional ball. I don't know if you remember when we proved it, we proved that your basis elements could be open balls or they could be open rectangles, and it gives you the exact same topology.
Yeah.
So now we have another way to talk about the exact same sort of topology. Maybe it's easier to think about it this way than it is as a 20-dimensional open ball. Maybe it's easier to think about the 20-dimensional open rectangle, however you'd say that. But yeah, so this generalizes. It's not true for just two topologies, it's true in general. And once you have the base case, then you can prove it.
With other dimensions. Okay.
Yeah, you can do a proof by induction now. So it's once you that's why we typically just prove it for two, because proving it inductively after that's real easy, right? You have the base case, and then for the case where it's K, when you take the cross product of K sets, that's still just a set, so when you cross it from with one more, now you're just crossing two sets. We already proved it works for two sets. So it's just like placing parentheses once when you go from your K to your K plus one case. Okay, so now let's talk about some common product topological spaces. So let I be the closed interval from 0 to 1, then I cross I is called the unit square. Crazy, right? And now we know the topology on that thing. We already had it as just a subspace of R2, but we're going to want to start thinking about these, instead of crossing all of R, just using a piece of it. You'll see that down here. So let's move on to another example. Let S, that's 1, S1 be the circle. Then we can think about the unit interval crossed with the circle as assigning intervals to circles or circles to intervals. Either way, we call I cross S1 or S1 cross I the annulus. And if we use an open interval, then we call it the open annulus. So let me try and make this make sense to you real quick. Two ways we can think about this cross right here. I could start out with a circle. Ignore my outer circle for a second. That's just to help me draw. So I just start with this inner circle. And then I'm saying to every point on this inner circle, I am going to assign a 1 unit interval. So to this point, I assign a 1 unit interval. To this point, I assign a 1 unit interval. To this point, to this point, to this point. And if I keep doing that, obviously what I end up getting is all this stuff in here, right?
Yeah.
We end up getting all those points. That's what we call the annulus. Or the other way to think about it is ignore the circles and just think about this line interval. You with me? And then to this point on the line interval, I assign a circle. To this point on the line interval, I assign a circle. To this point, I assign a circle. And I assign a circle. Looks terrible, but all the way, keep assigning circles, and I'll get the exact same space filled out. Now you might be thinking, yeah, but your circles are growing as you're doing that. Isn't that kind of cheating? There is no such thing as size in topology. There isn't bigger versus littler. We can't say that this interval is bigger than this interval. We can just say, oh, those are both intervals. Those are both the same in topology. We haven't gotten to homeomorphisms yet. We'll be doing that next chapter. But in topology, we say those are homeomorphic. They're the same. So there is no difference between a small circle and a big circle. In topology, the intuition was, all we maintain is proximity. So you think about a rubber band, there it is. And you think about the atoms in the rubber band as being points. If I take that rubber band and I bend it into a weird shape and pull it, so now it looks like this, it's still the exact same rubber band. And if this atom was next to this atom before I stretched it, that atom is still next to that atom after I stretch it. Right? I didn't move around my atoms. All the atoms that we're touching are still touching, or all the points that were close are still close. So they're topologically equivalent. They're homeomorphic. And we'll come over that in the next chapter, but so don't be disturbed by the fact that my circles get smaller or bigger. I still just assigned a circle. And you could have also thought about this as kind of like a little cylinder if you wanted.
That's how I thought.
Yeah,
And we
same
don't
thing.
have to change.
We don't use the word cylinder. We reserve the word cylinder for when we do R across a circle. Because when you do all of R, it goes on forever, right?
Mm-hmm.
So that's what we reserve the word cylinder for. So we call that the annulus. And then obviously if I would have used the open interval instead of the closed interval, then that would have just made this a dotted line on the outside and a dotted line on the inside, not including those points, right?
Mm-hmm.
Yeah.
So something like this. With these points included.
So annulus is the word for the shape of that?
Yeah.
Okay.
We call that the annulus. Next one we already talked about last week. The torus, a circle crossed with a circle. And this is supposed to be a bird's eye view. This is supposed to be a more natural looking one. But in either case, I have this circle, and to every point on that circle, I assign a circle. And I do that again and again and again and again and again and again. And that's going to leave me with the surface of a donut. You see that?
Yeah.
Would it be a hollow donut?
Yes.
Okay.
It's just the surface of the
It's
donut.
just the outline.
Just the outside. It's a two-dimensional figure, if you're okay with me saying that.
Yeah.
Like if you existed in that space, you'd be a two-dimensional object. Yeah. And then the disk, oh, we just used the disk without saying what the disk is. The disk is the circle filled in, all the points inside the circle, including the circle. That's what a disk is. So then if I do a disk crossed with the circle, instead of just a circle crossed with the circle, then we get what we call the solid torus, and now this is a solid donut.
Okay.
Make sense?
Disk is one-dimensional.
A disk is two-dimensional.
Two-dimensional. Oh,
Circle's
two-dimensional,
one-dimensional,
sorry.
disk is two-dimensional.
Yeah.
Okay. Make that squiggly line so I would remember to move my camera this time. And then, don't need the calculus stuff. Now, 2 more proofs and we're done. Yeah, good enough. All right. So our next proof, let x, y be topological spaces, let A be a subset of x and B be a subset of y. Let me draw a picture first. So we can have x cross y, and we can think about, let me say it this way. We can think about A cross B as a subset of x cross y.
Yeah.
So if you have x cross y as a topology, then you can give A cross B the subspace topology, where A is a subset of x and B is a subset of y, right? So you could use this topology to construct this topology. Or you could use x to create a topology on A, the subspace topology on A, use y to create a subspace topology on B, and then take A cross B and get it that way. So do you understand how I'm talking about 2 separate topologies here? So now let me read the statement, hopefully it makes sense. So let x and y be topological spaces, let A be a subset of x, B be a subset of y, let tau 1 be the topology on A cross B as a subspace of the product topology on x cross y. So that is a subset of that. And it inherits a topology from x cross y. And now let tau 2 be the product topology on A cross B, where A and B inherit the subspace topologies of x and y.
So if you had A1, B1, you're saying that's equal to A2, B2 on the other side.
Let me see if I can come up with a really explicit way to say this. So I can have x has its topology tau x, y has its topology tau y. I can have x cross y, which has its topology, and that's just the x cross y topology, the product topology. So that's what we've been talking about so far. Then I could come from just x, I could take A, and I could give it the topology A inherits from x, and I could take B and give it the topology that B inherits from y. This is what we did last week. And then I could come to this thing, and I could take A cross B and take the topology that A cross B inherits from x cross y. And then I could take the topology that I get as a cross product of these, which I'll call just A cross B for that topology, because I'm running out of ways to write this. So A cross B is the cross product of these 2 topologies. So the topology that we're talking about here is tau 2. the topology that we have over here is what I called up there tau 1. So tau 1 is a subspace topology A cross B gives as a subset of X cross Y with this topology. The other way we could have done it is taken A cross B as subsets of X and Y, given them their subspace topologies, and then take their cross product. So in one case we do the cross product, then we take the subspace topology, and over here we take the subspace topology and then we do the cross product. Either case we're going to prove we get the same thing. Follow that?
Yeah.
Okay.
Okay. Yeah, it's easy to get confused when you talk about so many topologies. So here we're talking about two topologies. I'm going to prove that they're equal. To do that, I'm going to prove one's a subset of the other. So one, V in tau 1. Okay, so if V is in tau 1, let's see, what was tau 1? Tau 1 was the topology on A cross B as a subspace of the product topology on X cross Y. So if V is in tau 1, that means V can be expressed as some open set intersected with A cross B. That's what meant to be the subspace topology. So if V is open in tau 1, then there must have existed some U in the topology on X cross Y, such that V can be expressed as that open set intersected with A cross B. You remember that for the subspace topology?
Yeah.
Okay. Now, since U is in the cross product topology on X cross Y, then there must be an open set, then it must be able to be expressed as a product of open sets, right? So then this gives us that there exists Ux and Uy such that V is equal to Ux cross Uy intersected with A cross B. Where this is an open set in X and this is an open set in Y. You follow that? Alright. That can be rewritten as V equal to U sub X intersect A cross U sub X, or U sub Y intersect B. Now notice that this is an open set in the subspace topology on A. What does it mean to be open in the subspace topology on A? It means that U can be expressed as some open set in X intersected with A. That's what meant to be open in A. Similarly, this is open in the subspace topology on B, because it's an open set in Y intersected with B. This is last week's stuff, right?
Yeah.
Okay, so that is in tau 2. What was tau 2? It was the cross product of the subspace topologies. Open set in the subspace, open set in the subspace. So you have open sets in the subspace, then their cross product is the same thing as the subtopology in the cross product space. I'm saying that terribly. Trying to think about a nice way to say it. Doing the cross product, then taking the subspace. So this V was, we first did the cross product, then we did the subspace. So this was open in the subspace on a cross product. And we show that that was the same thing as a cross product of things that are open in the subspace. And now we need to do the reverse. And the reverse is just like this. And that goes up to that, I think. Let's see. So if we take something in tau 2, what do we know? Tau 2 is a cross product
Of two.
of open sets in the subspace topology.
Yeah.
Open in subspace topology, open in subspace topology, take their cross product. When you have it expressed this way, you can rewrite it this way, right? That's just moving the intersections and the crosses around. That's what I showed you over here because I knew that we need to use it.
Yeah.
So that's going from here to here. Now, u sub x cross u sub y, what is that? That is some open thing u in x cross y. And a cross b is still just a cross b, so now we have an open set intersected. A cross b is an open set in the subspace topology on a cross b. Good?
Yeah.
Okay. That one didn't take as much space as I thought it would.
So all of that just proves that they're subsets of each other?
Yeah, so they're equal. I showed that B in tau 1 implies B is in tau 2, and B in tau 2 implies B is in tau 1. So therefore, tau 1 is equal to tau 2.
Okay.
So now what do we need? We need to show that the cross product of the interior is equal to the interior of the cross product.
I feel like we already proved that.
So now, let's go back to interiors. What was the interior of A? We also wrote it this way, A interior.
It's a union of all open sets in A.
This is the union of all open sets contained in A, right? So, notice that we're talking, this picture is implying three topologies. Interior on A cross Y, that is the union of all the open sets in X cross Y that are a subset of A cross Y.
Wait, A cross B?
Or A cross B, thank you. So here we're talking about three topologies. We have X cross Y with its topological space, we'll just call that one tau. And then we have the topology X with tau sub X. And then we have the topology Y in tau sub Y. So these are the only three topologies that we're talking about. A is no longer a subspace, it's just a subset.
Okay.
So these are the only three topologies we're talking about. So we're saying that in here, the interior of A cross B, so A cross B is a subset of X cross Y, right?
Yeah.
Yeah.
So A cross B, or the interior of A cross B, is everything in tau, is the union of everything in tau that's a subset of A cross B. Take all the open sets in tau, all the sets in tau, that are subsets of A cross B and union them up, that's the interior of A cross B. Right?
Yeah.
Maybe come back and talk about these ones first, and then say it
Yeah.
again. So now we've got some topological space X with its topology tau sub X, right? What did it mean to talk about the interior of A? Or, sorry, using this notation, interior of A. What was the interior of A? It's the union of all the open sets that are subsets of A, right?
Yeah.
Yeah,
Yeah.
I think so.
Yeah, that is what it is. Remember, we had it so that A interior was always a subset of A, was always a subset of the closure of A.
Okay.
Yeah.
Here's A. A interior is the union of all open sets contained in A. A closure is the intersection of all closed sets that contain A. So by definition, this is a union of subsets of A, and this is an intersection of sets containing A. Right?
Mm-hmm.
Now all we care about is this half of the picture. So the interior of A is going to be all the open sets in this topological space, or all the sets in there. Remember, what's tau? It's the collection of open sets. So tau sub X is all the collection of open sets on X. So the interior of A is the union of all the elements in here that are subsets of A.
Okay.
Similarly, the interior B try drawing one picture really quick. So we'll say down here is X, over here is Y. We'll say A is some subset in X, and we'll just pretend that we're using R as an example. And B over here is some subset of Y. These two intervals. So what is the interior of B? Let's make this one actually closed intervals. And we'll just think about in terms of standard topologies to keep it simple. And maybe we'll just make this one interval. Okay, so if B looks like that, what does B interior look like? It looks like the open interval like that, right?
Yeah.
Yeah.
If you think about this as R cross R,
Mhm.
just for the sake of an example, and A interior is equal to the open interval like that, right?
Yeah.
So here's B interior, here's A interior. A cross B interior is the interior of the cross product of this rectangle, so it's just the points in here. You with me?
Yeah.
So we're showing that all the points in here is the same thing. Well, when we do A cross B, let's see, we would have included this line, almost all of this line, and almost all of this line. Here's A cross B, and it includes its boundary points right there, there, and there. But the interior of this thing looks like this, right? So right here we have A cross B. Over here we have the interior of A cross B. So here's A. Notice it's closed there, open there. Here's B. It's closed all the way. If you do this cross this, you get this shape where we include some of our boundary points, we don't include some. But the interior of this thing is a rectangle where we don't include any boundary points. So the interior of A cross B is exactly what we would have gotten if we would have just done an open interval cross an open interval. If we would have just done the interior of A cross the interior of B.
Yeah.
So rather than, so you could have taken the cross product, then found the interior, or you could have found the interiors and then taken the cross product and you get the same thing.
Is that what we're proving?
Yes,
Okay.
that's exactly what this is saying. The interior of a cross product is a cross product of the interiors.
So your picture makes it really obvious, but does that work for any topological space? Like
Yeah, we just chose R to appeal to intuition. We're going to prove it in general. And we're proving it for the interior. It's also true for the closure.
Yeah, that makes sense.
And the intersection of the closure, the intersection, the cross product of closed sets is also closed in this topology. That's something else that I should have mentioned that I didn't. And that's going to prove at the end of class if we wanted to. Maybe I'll see if you guys want to do the proof. If you don't, I'll just explain it. So let's stick with this for a second. So I wrote that arrow because I thought going that way was real easy for some reason. So let's start by showing that this is a subspace, or a subset of this. And then I'll show that this is a subset of this. Okay? So let's see. Observe that A interior is open in X and B interior is open in Y, comma, so A interior cross B interior is a cross product of open sets. Of open sets and therefore open. Right?
Right.
Because by definition of our basis on this cross product topology, it's a cross product of open sets. So that's actually a basis element. Right? Since A interior is a subset of A subset of B. That gives us that A interior, exactly, cross B interior, the subset of A cross B, which gives me that this is a subset of this, right? So remember, what is the interior of A cross B? It's the union of all open sets that are subsets of A cross B. I showed that this set is open, and I showed that this set is a subset of A cross B. Therefore, it's a subset of this.
Yeah.
You follow that? Are you getting confused by me using this switch between the circles and the interiors?
No, I understand.
I just have to use it on this one because how do you do the interior of a cross product?
Yeah.
Like A cross B interior? So I'll use the actual int for when I'm doing 2. Okay, so now let's go the other way. Let's see. This one might be easier to just get a point. So now we're going this way. Well, this isn't an if and only if we're just showing subsets, but oh well. So now let A comma B in the interior of A cross B. Well, if A comma B is in that interior, what does that mean? That gives me that there exists U, I'll write down here. So since A comma B is in here, then A must be in an open set that's a subset of A, and B must be in an open set that's a subset of B.
Yeah.
Right? So that gives me that there exists U in tau sub X. Did I call? Yeah, I labeled X somewhere out there. Alright, so there must be U in tau sub X and V in tau sub Y such that A is in U is a subset of A and B is in V is a subset of B, right? Which gives me that A is in the interior of A, and B is in the interior of B, which gives me that AB is in A interior cross B interior, which gives me that the interior of A cross B is a subset of A interior cross B interior. So let's make sure we understand that. Grab some random point in the interior of A cross B, and I need to show that it's in A interior cross B interior. So grab some arbitrary point in that interior. Now, since little a is in A, there must have been an open set containing it in X. And since little b is in big B, there must have been some open set in Y containing it. So I know that A is in some open set in X is a subset of A, and little b is in some open set in Y containing, or that's a subset of B. Now, since I know that A is in an open set that's a subset of A, then A is in the interior of A. Similarly, since little b is in an open set that's a subset of big B, then little b must be in the interior of big B. And since that's in the interior of that, that's in the interior of that, then their ordered pair is in the cross product of the interiors, and that's what we were after. So, I guess we can write the last line. Therefore, the interior of A cross B is equal to A interior cross B interior. And now we're done. Any questions on that?
No, that was pretty straightforward.
Okay, and then so the same is true of the closures. And then the last thing I was going to prove for you guys, if you want, but make sure I at least tell you, so I'll just tell you, and then you decide if you want me to prove it. The intersection of closed sets is closed in the product topology. So if I know that C is closed in X, and I know that D is closed in Y, then I know that, oh, did I say the intersection? I meant the cross product. That C cross D is closed in the cross product topology on X cross Y. So if C is a closed set in X and D is a closed set in Y, then C cross D is a closed set in X cross Y. Get a picture for it real quick for on the real numbers. Take a closed set in R, take another closed set in R. Now take their cross product. Their cross product is going to be a closed rectangle in R2, which we know is closed. Yep. So that's a specific example. So you want to see the proof of that, or you guys getting kind of burned out?
We can see the proof. I'd like to see it.
The proof?
Yep.
Okay. So let's prove it. So, proof, let's see, let X, Y be topological spaces, and let, I'll just use C and D, I guess. Let C, comma D be closed in X, comma Y, respectively. Then C cross D is closed in X cross Y. Okay. So so we're trying to show that maybe we don't need to wrap the words for this, we can just write what it equals. I'm trying to show that C cross D is closed, right?
Yeah.
How do I show it's closed? I need to show
Its complement is open.
its complement is open. So let's look at the complement of CD. So observe that. So what's the complement of C cross D? That's going to be X cross Y minus C cross D, right?
Yeah.
So I need to show that this thing is open.
Okay.
Oh, that's too easy. So this is then equal to the same thing as X minus C cross Y minus D.
Yeah.
Which that's open. Because C is closed in X and D is closed in Y. That was a lot easier than I thought it was going to be. Did I cheat somehow?
I feel like you proved the same thing for
I have, here's X, here's Y, and I have C. Let's see, C was an X, so we'll make that C. Now let's make it use boundary points. So I'll make this part C, and I'll make this part D. So X cross Y minus C cross D is going to be all of this. We take all of X cross Y and then we get rid of, well, oh, that was my start of my set. Oops. Let's see, X cross Y is so I take X cross Y and then minus C cross D. That is this area. x cross y, and then get rid of c cross d. X minus c gives me this. Y minus d gives me this. Okay, those are not the same thing. That makes more sense. That was too easy.
Yeah.
You see how those aren't the same?
Yeah.
Because x minus c cross y minus d is just this area. So let's see what we missed there. We missed y minus d cross c. And we missed x minus c cross d, get it in the right order. So we missed x minus c cross d, and then we missed the other one. Okay. And then we missed
Y minus,
c cross y minus d. Right?
yeah.
Okay. That's better. Okay, so obviously this one's open, so we're done there. Let's look at over here. Over here we have an open set crossed with a closed set. We're saying an open set crossed with a closed set is open.
Don't you have the same thing with the Y?
Say that again?
You said that one is easy because it's open.
Yeah, this one is for sure open, because
Oh,
it's an open set crossed with
That
an
one.
open set.
okay, yeah.
This one we have an open set crossed with a closed set, and this one we have a closed set crossed with an open set. And how can I say that those are closed? I can't say that those are closed. So now I wonder if I wrote the problem wrong.
Even with the picture you drew, x minus c cross d would still be wrong, because didn't on the left side you have dotted lines and it would have to be solid line if it was truly x minus c cross d.
Let's get that picture back up. And this time we'll keep it simple. We'll just do x to there, y to there. So x comes out to here, y comes out to here. And we'll do c, d like that. Now c and d are closed. And x and y are the whole space. So x cross y should actually be a solid line, because this is the whole space. C was an x, D was an y. We're subtracting this. So let's draw the space that we're talking about. So in the space that we're talking about, this is a dotted line. And we're saying that that can be expressed as x minus c, which is that, crossed y minus d. So x minus c, that's not including that. Y minus c, that's not including that. So this is x minus c cross y minus d. So now, what is this set? We need to include that line and include this line. That's just d crossed with x minus c.
X and y are open, right?
X and y are the whole space, so yeah, they're open.
Okay, then aren't those lines supposed to be dotted?
These ones,
Yeah.
they're the edge of the space, so it doesn't matter if you dot them or not. Do you want your space to include those points or not? You can keep them dotted.
No, I just, then this would be a really specific example, and then showing it works for this one doesn't necessarily mean it works for all the other ones.
Well, the tricky point is I need to get the points that I missed here, here. So this one, when I include those points, So basically I need to include the points there. Probably better keep that drawn in. So this, but not that, is what this one is, which needs to be x minus c cross d. So x minus c, that's going to be open, so that's an open interval, cross d, a closed interval. That makes sense. But now I need that to be open. And is it open?
Is an open set crossed with the closed set open?
Oh, here's how I think we want to think about it. That's going to be x minus c. Okay, I think I got it. Do brackets so you can see it. X minus c cross y union y minus d cross, or x cross y minus d. Okay. X cross y minus d. Okay. So x minus c is this, crossed with y gives me everything up like this. And then I union that with y minus d cross x, which gives me that.
Okay.
Right? So now let's make sure that that actually makes sense and our picture didn't just do it for us. So everything in x and y, x cross y that's not in c cross d, is everything that wasn't in c but in y, or everything that's in x but not d. Okay, that actually makes perfect sense. If I'm going to exclude all the points with these, if I'm going to exclude these coordinates, so if we think about this in coordinates, I want to look at all the points that aren't this specific square. So I can remove all the points that had this as their x coordinate, or I can remove all the points that had this as their y coordinate.
Okay.
Does that make sense?
Yeah.
I think that's the right way to picture it. So if I remove all the ones that had this as their x coordinate, or all the ones that had this as, how's the right way to say that? Not the ones I'm removing, the ones I'm going to keep. I'm going to keep all the ones that didn't use c as an x coordinate, or y or d as a y coordinate.
Yeah.
Maybe if we think about this in terms of it's not, so when we negate this, the complement of this, to make it an and, no.
What you have makes sense, yeah.
Does it?
Yeah.
Okay. And then once you got equal to this, open, 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 union of opens is open.
Yeah.
So the whole trick to that is proving that this set and this set are the same thing.
Okay, wait.
No.
Is your set supposed to be closed? What?
This is closed, so I need to prove that this is
Oh,
open.
you're showing that the complement of a closed set is open.
Yep. So this is closed, so this is open. This is the same thing as, this is closed. We need to show that this is open, but this is the same thing as this. This is open, so this is open, so we're good.
I see, okay. Makes sense.
You're saying we assumed C cross D is closed, and we proved that.
Its complement is open. No, we didn't assume it was
That just comes-
closed. We assumed that C was closed and D was closed. We were
Oh,
proving that
okay.
C cross D was closed.
Okay.
So since that's how I know that this is open, and that's how I know that this is open. It's because I know D's closed, so this is open, C's closed, so this is open, open cross open is open, open cross open is open, union of opens is open. Okay. So yeah, that wasn't too bad. But glad we thought that through and didn't do it wrong. Okay, any other questions? Alright, so next time we'll be talking about the quotient topology. For those of you from discrete math, a similar concept that we use there is equivalence classes. So, if you can't catch up on quotient topologies, I mean, you could just Google that and read about it, and that would be enough to already familiarize yourself with it. The reason I want you already familiarized with it is because these quotient maps that you use to create a quotient topology are never going away now. We're going to be using them left and right all the time. And so they're crucial that you get comfortable with them. They're the first functions that we're going to be introducing. Up till now, we've just been talking about sets, basically. So now we're finally going to be taking a topology and applying a function to it to get a topology.
Cool.
And then when those functions have certain properties, then we can finally
Now we're
call them
applying
continuous.
topology. 2 weeks.
Yeah, so there's two major... Topology was a minimum structure you needed to capture two very important ideas. The first one is convergence. And we already covered what that meant in this class, to have a sequence converge to a point. That's the underlying idea behind a limit. The second major idea that we cover in topology is a continuous function. Now in calculus we express a continuous function in terms of a limit, and we'll prove that's logically equivalent, the calculus definition. But actually continuity is a much, much simpler concept than what we talk about in calculus. There's a very simple way to talk about in topology, what it means for a function to be continuous. So a topology is the minimum structure that we need to start talking about convergence and what a continuous function is. We've already talked about convergence. We're going to get to the point where we say a continuous function. We got next week, we'll do quotient topologies, and the week after that we'll start continuous functions and homeomorphisms and what it means for two topologies to be the same. So, getting close. If you can get yourself familiar with quotient topology, that would be very good.